So the first concept we're going to look at are so-called summations. So let's talk a little bit about summations today. So I'm just going to make some notes. I encourage you to follow along. So often we encounter series given an infinite, I'll put that in parentheses, infinite or finite sequence. Terms of the sequence are added or multiplied together. So the way you got to look at this is I give you a bunch of terms that are going to be part of a sequence. So for example, the set of all even numbers, a sequence of those would be 0, 2, 4, 6, 8, 10, and so on if I wanted all the non-negative even numbers, for example. That's an example of a sequence. So in a series, we're going to be interested in where we have a sequence, and I'm looking at if all those terms are added together or multiplied together. Seems pretty nice and simple. So I'm going to talk about summations first. So given terms a sub 1, a sub 2, all the way up to a sub n. I'm going to assume this is a finite sequence, but it doesn't have to be. Their sum, which is what we would call a finite series. A finite series can be given by the summation which we'll denote with sigma. So sigma as follows. So I'm going to have sigma, and I'm going to have two numbers here. I'm going to have what we call this the lower limit, and we're going to have n here is going to be the upper limit. And I'm going to denote this with a sub I. You can look at I like an index. And this is going to represent a sub 1 plus a sub 2 plus a sub 3 plus all the way up to summing over all of these to a sub n. So when you look at this, you should read it as the summation from I equals m to n of a sub I. So if you look at this lower limit, upper limit, you can think of, like, if you want an easy way of thinking about it, you just think of it like a loop where I'm going from m up to n, and I is the index, just like if you had on a for loop. So it's nice and intuitive and easy to understand. Okay, so that's what a summation looks like. So I'm just going to give you an example of what I mean by one of these. So just as an example, if I give you 1 plus 2 plus 3 plus all the way up to n, this would be the sum from I is equal to 1 to n of I. So notice that my I here is each one of the numbers from 1 all the way up to n. So notice it starts at 1, goes up to n. So often this series, by the odd chance, often is called the arithmetic series. Now, it's worth noting, just as another bit of terminology, if you're wondering what this is called, I said that this is the lower limit, that's the upper limit. This is often called the sum end. Sum end. It's a fancy word. Don't worry too much about the technicalities of these things. I'll give you another example. This time I'll give you an infinite series. Infinite series I'm going to talk about is so-called the harmonic series. This is another one if you've taken an analysis course or a sequences and series course, you will have seen this at some point. Don't worry if you've never seen it before, that's fine. So it is the sum from k is equal to 1 to infinity. So that's how you know right away it's an infinite series. You see the infinity symbol there of 1 over k. So what does this mean? It means, so I read the k here, I put it in for 1, I get 1. When k becomes 2, then this is 1/2. Then when k is 3, this is a third. When k is 4, it's a quarter, and so on. And it's an infinite series. So there's an infinite number of terms here on the right-hand side. So this is just an example, just showing you an infinite series. Some of these actually have sums, some don't. I'm going to give you another example of another series, but I'm going to give you a version with a product instead of a sum. So I'll say similarly, a series that is a product of each term, we're going to use, instead of sigma, we're going to use capital pi, this big pi, is as follows. So here's just an example of if I wrote out a product. So I'm going to have a lower limit of 1. I'm going to have upper limit of n. And a sub I is the term right there. Now, it's worth noting that this is still a lower limit, that's an upper limit. But now instead of it being where I'm going to sum over them, I'm going to multiply over them. So the easy way you can remember this one, if you see the pi symbol, you think product. P product. Nice and simple. So this is a sub 1 times a sub 2, a sub 3, all the way up to a sub n. Nice and easy. So far I've just been covering notation. I'm just going to give you one example of applying this notation. So I'm going to let n be a natural number. So I'm just going to assume that that includes 0 just for our purposes. I'm going to define what is called factorial. I'm going to have n factorial, which is denoted by n with an exclamation mark like this, is the following. So I can define n factorial using this notation as follows. So you may have seen n factorial before, but let me write it out using this notation. So lower limit is 1, upper limit's n. It's going where the term here is going to be k. And I'm going to have n times n minus 1 times n minus 2, multiplying all the way down to 2 times 1. That's n factorial. So I'm going to give you some properties. Of summations. That S sort of melted in the microwave. And products. So I'm going to show you a bunch of neat little properties you can use. So I'm going to define, I'm going to say if a sub m plus 1 dot 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 and b sub m comma b sub m plus 1 dot 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 and so on are sequences. Remember, a sequence, think of it like all the odd numbers or all the even numbers. say non-negative ones. You have some starting point and you kind of go along and you have a sequence of numbers. Okay, our sequences of real numbers. So I'm going to keep this rather general. So we're going to be talking about real numbers here. So these can include your counting numbers, rational numbers like fractions. It also includes the rational numbers like square root of 2. And C is any real number then the following equalities hold. Whoop. One quantifier I want to add on here. For any n greater or equal to m. So I'm going to have these three properties I'm just going to list here. I'm just going to state them as fact as opposed to proving them for you, just because it's not going to be too important for us to prove these formally. But you should be able to convince yourself using algebra that these should hold. So I'm going to have a sum from k is equal to m to n of a sub k. And I'm going to have another sum. I'm going to sum these two summations here. So I have two summations, each with their own sums within them. They each have an own sum end. What I can do is I can actually lump them together like so. So if I have two separate sums like this, I can actually combine them into a single sum. Likewise, you can clearly see this is an equality, so I could decompose, or there's a fancy word for this. I'll let you think about it. What is it? Distribute. You can distribute over a summation like this. So if I have two terms I'm adding in a sum, I can distribute over a summation. So now I get two sums instead of just one complicated one. So that's a handy property to have. Just don't forget about this one. This one's really handy for algorithm analysis. So another one is if I have C times the sum from k is equal to m to n is actually equal to the sum from k is equal to m to n of C times a sub k. So another very handy property. Now I wrote it this way just so I want you to think about this. Remember this being an equality here. So oftentimes you'll encounter where you have some constant times something interacting with this kind of iterating variable here, this k here. So this might be some counter, like when we had our example with the 1 plus 2 plus 3 plus 4 all the way up to n. We might have like I times c. Notice that c has no relationship with the terms inside. So what happens is you can look at it as each term. So if you're not really convinced by this, write this out from, you can have a sub m plus 1, a sub m plus 2, and so on. And you'll notice each one's multiplied by c. So you can actually factor out the c from all of these terms, and you get what's here on the left-hand side. So isn't that handy? Third one, this is one involving products. So if I give you a product such as this, and I'm multiplying it by another product like this, it's going to be very similar to number one, except it's going to be carrying over multiplication. So it's going to have a product. Again, if you're not convinced by this, just write out what these series would be and rearrange terms using associativity. So you'll notice that now I can distribute over a product using this. So these are just a few properties I wanted to point out for you. So I'm going to talk a bit more now about closed forms. Now, very often, when we actually talk about analysis of algorithms, we very often need to have this nice thing of a so-called closed form formula or closed form. sorry, closed form expression. I get a little excited here. Now, very often you'll notice these sums here, sometimes they have many terms to them. And I would like to have a nice simple formula that I can calculate using a constant number of operations to evaluate and determine the total sum over a summation like one of the ones we've seen. So that's the point of one of these closed form expressions, is that I can evaluate it using a constant number of operations, as opposed to having the sum over that whole thing, which isn't as pretty. Sometimes it exposes asymptotically the behavior of what the function that represents that sum looks like, at least from our context. So I'm going to talk about some common closed forms. So let me just list these out. So these are for your reference. So the sum from I is equal to 1 to n of I. So the arithmetic series, this is equal to n times n plus 1 over 2. At some point, I will give you a proof by mathematical induction to show you this one is in fact true. So this is the arithmetic series. This one I would expect you to pretty much remember after a while. Again, here's another one. Sum from I is equal to 1 to n of I squared. So this is just the squared term, so it's just I where I square it. This is equal to n times n plus 1 times 2n plus 1 all over 6. Looks, it's not as clean as the other one. This one should remind you a little bit of one of the properties I showed you over on the left side. Here's one I would expect you to usually remember. It's based on basic counting rules. So I'm going to assume A and B are integers. And I'm going to assume that C is just some real number. And that A is less than or equal to B. Then the sum of I is equal to A to B of C is equal to C times B minus A plus 1. Now, I'll give you some justification for this. So notice the lower limit here is A, the upper limit is B, and notice I'm summing over C's. So I'm going to have C plus C plus C plus C, but how many times is C going to occur? Well, it's actually going to be B minus A plus 1. Now you might ask where the plus 1 came from. It's actually because when you count an element in itself, you have to make sure you include the one that you, because when you take a, say if you have, let me just draw a little picture for you. Say for example, if I had like B was 5 and say A was equal to 2. So you'll know that it has to be 2, 3, 4, and 5. Now you would agree with me that B minus A is in fact 5 minus 2, which is equal to 3, right? But remember, there is at least one other element I haven't counted if I were to take all the terms. It's the lower limit that I didn't count for. Or it could be any one of the elements. The point is that if you actually want to count up the number of elements, the number of times I have to go through this, it's not that it's actually the subtraction of these two. It starts at 2, then 3, then 4, then 5. It includes one of them. You go, like I said, go back to the analogy of the for loop. You can think of it like where I have a my upper bound on my upper limit here is a less than or equal sign, not a less than sign. So I have to include the upper limit and my count, or lower limit, respectively. Okay, so that's where this comes from. Just think of it how many times you have to count all the elements. And the C, that's just actually from this property I showed you over here, the property number 2. Okay, let's go for another one. Property D, here's another one. If I give you a product, so I'm going to have lower limit is 1, upper limit is n. I'm going to have I times I plus 1. This is actually equal to n times n plus 1 times n plus 2 all over 3. I don't have any much interesting to say about this one. Now, I also do have a version of the arithmetic series in my list as well. That's number E, or item E. Instead, I'm going to skip right to F, and I'm going to put it over here. So let me put F here. This is the last one in my list. So I'm going to assume some real R not equal to 1. And I'm going to imagine I have the following finite series. Now, it's worth noting that there is an infinite version of this, where the upper limit is, in fact, infinity. So I'm going to imagine I have two numbers, L and U. And I'm going to have A times R to the I. Or remember, R is some real number that is not equal to 1. So this right here is, in fact, equal to A times R raised to the L minus R to the U plus 1 all over 1 minus R. Now remember, that's a capital L right there. It's not a 1. You might know this one. This is called the finite geometric series. Every once in a while, you will run into this one. You will be warned. It sometimes pops up. So those are all the interesting ones I really wanted to point out. I'm going to point out a couple tricks that you could do with summations, just to give you a couple tricks. Because I just want to make sure that, because when you're manipulating summations, sometimes it's a little unclear what you could do with summations. Especially when you just see some daunting looking thing and you're like, okay, well, how can I simplify that down? Because oftentimes the goal is to get a closed form. So that you could say something about, say, a running time of an algorithm. Okay. So I'm going to give you some tips on how you can do. So I'm going to call this simplifying summations. We'll call it simplifying summations. Simplifying summations. So I'm going to give you some tips. So you can think of these as common tricks you could deal with summation. So the first one I have is, and this one should remind you of the first tip I gave you. Multiple terms inside a summation. Can be distributed. Remember, that's that fancy word. Distributed into multiple, that I sort of melted there. Multiple summations. So what we're going to do is, the tip is, if you see a very complicated summation, distribute it into a bunch of smaller summations if you're not sure what to do with it. Just as an example, imagine I give you the sum from I is equal to 1 to k of I minus 1. Now, because of property 1 that I showed you in my list of properties, you know that you could split across this summation, because really you could look at this as plus negative 1. And bam, now I have two summations. I is equal to 1 to k of I minus the sum from I is equal to 1 to k of 1. And now I already know what this looks like. I know what this looks like. These both look like ones in my list. Let me just remind you. Let's go back over to my list here. So I have actually both of these summations. They look like things that I've already shown you. So let me just get to go a little bit further over there. Just a little further. Okay. That's good enough. Okay. Note, does this look a lot like the first summation? And this one looks a lot like the second one, right? So let's go back over here and let's apply those closed forms to these simplified summations. So let's see what we could do. So notice that I have this I here. The upper limit is k. So I can write this as k times k plus 1 all over 2. So that one deals with this first sum. The second one here is just like our one we had before. What we need to do is look at this. You can think of the c as 1. So I have 1 times something. What was the something? It was upper limit minus lower limit plus 1. You want to count up how many times the 1 is getting added. So it happens how many times? K minus 1 plus 1, which makes sense because it should occur k times. Because it's 1, then 2, then 3, then 4, then 5, which is all the way up to k, which is k times. So I have minus k minus 1 plus 1. This is just k, right? Then I can simplify this a little further. So I'm just going to make this a little easier to play around with, I'm going to make a common denominator across these two. So I'm going to have 2 like this. So I'm going to multiply this by 2 so it has a common denominator. So I'm going to have k squared, because this will be k squared here. So it's k squared times, it's k times 1, which is k, right? So I have k squared plus k, and this is just k here, so it's minus k, but now I have to multiply it by 2 to make it a common denominator. So it's minus 2k. But what's this? What's this? What's this? This is just k squared minus k, because remember it's k minus 2k, that's minus k. Because I'm only left with 1k left, right? And I subtract, that's all over 2. And bam, I can factor out the k here. I got k times k minus 1 all over 2. See, it's not too hard. It's not hard. Is that nice? So if you see a summation, you're not sure what to do with it, and it's a sum like this, try breaking it apart into simpler sums. That's my first tip. My second tip is that sometimes it is good. I don't like using the word good because good and bad are subjective terms. Sometimes it is good to write out what the summation means, then group related terms. So then group terms. Just as an example, I'm going to show you something that looks really complicated, but with a small little bit of hindsight, we can actually make it look really simple. Okay. So I'm going to have the sum from I is equal to 1 to 400. Well, it's so far a little daunting. I'm going to have minus 1 raised to the I plus 1 times I over 2. Now, these symbols here, if you've never seen them before, those are ceiling. That means ceiling of I over 2. This means round up to the next integer if it's a fractional part. Likewise, there also exists this thing called the floor. Looks like this. It means round down. So if I have a fractional number and I see the floor, I round down. If I see the ceiling, I round up. Okay, so this looks a little bit daunting here, but let's just write out what it says. So let's see what this says. So I start off with 1, and I see minus 1 raised to the 1 plus 1. So it's minus 1 squared. If you may remember, if I have something like minus 1 squared, if I take the square of a negative number like that, I should end up with what? I should end up with a positive number. And whenever it's odd, it should be negative, right? It flips the parity. flips from positive, negative, positive, negative. Well, technically not parity, the sign. We'll see an example much later on where we're dealing with parities. Anyways, so if I write this out, I'll let you think about it. It's 1 minus 1 plus 2 minus 2 plus 3 minus 3 plus 4 minus 4 plus all the way up to plus 200 minus 200. So do you see what's happening now? If you actually look at this and you try out each one of the terms for a little while, you start seeing the pattern. Notice that I'm adding a term, then I take it away. I add it and I take it away. And I add it and take it away. So if I rewrite out this sum, you'll notice that I'm going to have a bunch of positive terms. So these are all my positive terms. Then these are all my negative terms. And now I know what to do with each one of these sums, right? Now if you already knew the hindsight here, you know right away the result, but I'm just writing it out just so you can see how I manipulate the summations, okay? You'd probably be able to look at this and be like, okay, I already know the answer, but I just want to show you how I manipulate the summations, because it may not necessarily be the case that these are 200s. You might use this idea somewhere else. So this would be 200 times 200 plus 1 all over 2. Remember, that's just a closed form that I'm applying. Let's do the exact same thing. Minus 200 times 200 plus 1 all over 2. This is equal to 0, right? Because I add the term, then I take it away every single time. And why is that true? It's due to symmetry. Every single time I have all my positive terms are actually equal to all the terms I'm taking away. So so by symmetry, they cancel each other out. Okay? So that's another trick I can give you. So I'm going to give you two more. So the next one I'm going to do with you is the one that you should get used to if you get something that doesn't look as pretty and something the thing you really want. Because oftentimes I'll have summations. You notice all the ones I gave in this example, they all looked really nice and easy to apply the closed form expressions, right? Well, sometimes you get things that don't quite fit the mold, but you can easily modify them to get something that looks like it. So you can add or remove terms. So I can add or remove terms to, in quotation marks, massage the summation into a closed form that is known. That's all I'm going to do, is I'm just going to take and add and remove terms. So I'm going to massage the summation so that I could pop something in or push something out, so I could get something that looks like something I would like to have for my closed form expression. So here's just an example. It's nice and simple, but it should give you the idea pretty quickly. So imagine I give you a sum with the lower limit is 3. So from I is equal to 3 to k of I. Now, if you've seen this, you know, okay, I know what this looks like when I is equal to 1, right? But I don't know what it looks like when I is equal to 3. So what am I going to do? I'm going to try to make it look like I is equal to 1 by doing something else. So remember, this is 3 plus 4 plus 5 plus all the way up to plus k. Now, to get the thing I would like this to look like, it's 1 plus 2 plus 3. So notice that I need those 2 extra terms I need to put in there somewhere. So notice that this is in fact equal, if I massage this. Now, besides, massage is not really a formal term. I just like to use it because it gives you the idea of what I'm going to do. So I have the sum like this. And I'm going to subtract off those 2 extra terms that I was trying to massage by introducing them. So by introducing them here and getting rid of them after, I can get something that looks like something I can work with. But what's this? That's k times k plus 1 all over 2. What's this? That's 1 plus 2. That's equal to 3. Boom. Isn't that nice? So just think about it. If you see a form that looks like something you want, a very powerful and simple idea is all you need. Massage the summation. Okay, now this one is, I would consider, the more technical of these 4 techniques. And I guarantee you, if you've taken a class where you had to see summations before, somebody would have shown you this trick. I'm personally not the biggest fan of it, but it's very powerful in its own right. It's not very powerful in the sense compared to some of these other techniques. So modifying the lower and upper limits to obtain a known closed form. So just like in my previous example here, notice I started off with I is equal to 3. It'd be nice if that was equal to 1, right? Now, what I would like to do is I would like to be able to change what these upper and lower limits look like so I can manipulate it like it looks like the form I would like it to look like. So here I'm going to give you an example. Some choo-choo time. So assume k is greater than or equal to 2. I'm going to let g of k equal the sum from I is equal to 3 to k plus 1 of 2y plus 2. Now, if I showed you this right off the hoot, there are several things you could try to do, right? You could try this third technique here. You try to massage the summation. That would work. I'm going to try something else here. I'm going to try to manipulate the upper and lower limits of this sum so it looks like something I could easily manipulate using the first trick I did. So I would like to make this into a 1. I'm going to let j, so I'm going to assume another variable called j, and I'm going to make it equal to I minus 2. Now you might ask, Dan, why are you picking I minus 2? Remember, I want to make I equal to, I want to make this 1 here. So what I would like to do is I would like to take 2 off of it. That's where it's coming from. So update the lower and upper limits and inside careful. The inside part is most important. Oftentimes students will forget to update the inside, the summand. That will cause a lot of problems down the line. You'll get an incorrect sum, most likely. So what's the lower limit? If I want to make it so that I can use, let me think. I would like to make it so that j, because I'm going to introduce j as now the lower limit, this variable. So I want to make that look like 1. So I'm going to say the lower limit that m sort of mutated there. The lower limit is j is equal to 3 minus 2, which equals 1. So you'll notice that the difference here, I'm going to try to put j there, but by knocking everything down by 2, I have to do that everywhere. But when I bump things down, it actually causes another effect inside the sum. So let me take a look at that. So j is equal to 1 there. The upper limit. So remember, I knocked down the lower limit by 2. So the upper limit also has to get knocked down by 2. becomes k plus 1. Remember, that's what the original upper limit is. I'm going to subtract 2 from it and end up with k minus 1. Why do we need to have it so we update both of these? It's because we need to make sure that there's the exact same number of terms I'm summing. However, we have to be careful because now I'm going to put everything in terms of j instead of I. Now, I bumped everything down by 2. But what happens inside? And the summed becomes, it becomes what? Well, remember, it's 2i plus 2. Now, wherever I see I want to put j's. But what's j? Well, if you rearrange this equation here, I would need to add 2 to both sides of this, so it's I equals something over here. So when I bumped everything down by 2, what actually happens is I actually add 2 to the summand inside. So if you're not convinced, just take j is equal to I minus 2, rearrange that so it's in terms of I. So we have I is equal to j plus 2. Just add both sides to the equation there. So you get this, which is going to be equal to 2 times j plus 2 plus 2. And this is through rearranging on that equation over there. If you're wondering, the name of this technique is substitution. I'm just substituting one variable for another. So through substitution, we obtain that now we obtain this new sum. J is equal to 1. The k minus 1, remember this is the updated lower limit, that's the updated upper limit. And then I have 2 times j plus 2 plus 2. The summand has been updated. If you do some algebra, you'll end up with this being j is equal to 1 to k minus 1 of 2j plus 6. And now at this point, you can apply the techniques that you'd seen previously. So I encourage you to try the other techniques. Try the other techs to finish this. So notice that now I have something that I can easily apply I could distribute that into 2 sums and simplify it and the way I did it before. Isn't that nice? So this fourth technique is really handy if you have very complicated sums. So sums that just do not play nice with you. And it's really unclear what you can do with it. So that's all I have to really say about summations. It's worth noting that when you have a double summation, one point of contact you should really be careful on is you have 2 sums. Like if you give you 2 sums that look like this and you have some term right here, it's worth noting that the sum here and the sum here, you can switch the summations around. Sometimes that's handy to do. Another thing worth noting is that if you're summing over them, you got to think sort of like the intuition I really like of nested for loops. So if I'm summing over this, if there's a variable that's related to if there's something over here, think of this like the outer loop, this is the inner loop. Let's say this was I and this is j. If j relates with I, like say the upper limit of this is, say I. So I'm getting really excited here. That you have to be really careful because you got to look at I like a constant inside here, like you're evaluating this sum. Hopefully I'm clear. So you can give that a try if you're curious about it. Feel free to ask me any questions about that if you'd like.